So, we are we have been working on this tight binding approximation for certain lattices, and we concluded with the band structure of graphene, which is also shown in this view graph here. Here, for example, this epsilon naught has been taken to be 0, which, as I said, is setting your energy scale. So, your Hamiltonian will become this 0 f k, f star k and 0, where f k is basically the this kind of thing, or we have done it already here. So, either way you will finally get a spectrum which is this, which is the same as the one that is written here, the one that we wrote here. This is the spectrum. So, so one can then plot the wave function, the f this spectrum, and as we showed, the spectrum gives this kind of two states, one coming from the bonding contribution, another coming from the anti-bonding contribution. Now, there are other interesting systems that people talk about these days. Graphene, of course, is famous for its Dirac points, as we mentioned, that you have a massless Dirac spectrum at these points, linear in k and k prime. Whereas, there are other interesting objects that have been discovered in the last couple of decades, and these are really in our last 30-40 years, these have become some of the major issues in research, and major these are, for example, in nanosystems and nanosciences, these kind of small structures, ultra small structures, nanoscale structures are studied repeatedly, and they are extremely important in terms of the applications point of view. Now, there are two very common carbon nanotubes. Carbon nanotube is nothing but a graphene folded into a tube. So, graphene sheet folded into a tube. So, although this came earlier than graphene, single sheet graphene, single layer graphene was only in the last couple of decades people have been able to use, but this nanotube is in existence for a little more time. This came earlier, and there are two kinds of arrangements. As you can see, this tube can be the graphene sheet can be folded in two different ways, three different ways actually, but these two are the major ones, the armchair and the zigzag. So, the name comes from this the red, you can see the red part here, and how this red part is arranged, and in the chiral this is arranged in this fashion. So, and people have actually calculated their band structure. It is straightforward to do it. If you know how to do graphene, you can also do this one, and the band structure of these two are interesting. You look at the armchair graphene, this has this point, whereas in the zigzag graphene you have the gapless regions here and here. The band structure is completely different. So, that is that's interesting, because it is the same structure just folded two different ways, and the band structure becomes completely different. So, I will not belabor much on this, but this is just an illustration as to how different things can be by just changing the geometry a little bit. Let me also again go back to this point that I raised, that there are instabilities of the Fermi surface. So, Fermi surfaces of this kind, for example, this blue one, this square Fermi surface, this kind of Fermi surfaces are unstable towards distortions or other instabilities, some long range orders, because these kind of Fermi surfaces can be brought onto each other by just look at these Fermi surfaces, this one, the square one. So, this is pi 0 0 pi, these points. Now, you can see that there is a q vector and another one here. If you translate this one of these flat regions of the Fermi surface, which is a line here, by the q vector, then your and this q is basically pi, this q here is pi pi, and you can check for yourself that if epsilon not equal to 0, then E at pi pi. So, what is so E at pi pi is minus E at 0 0. So, that means E of k plus pi, k plus k x plus pi, k y plus pi in this band structure at with epsilon not equal to 0, epsilon not equal to 0, this thing happens is equal to minus E of k x k y, and that means these two energies are just negative of each other, and they are at the so these are at the Fermi surface. So, the both the energies are 0. So, both are 0 here. So, the so this is, for example, on this line. So, this is not 0, on this line your energy is 0. So, you can take an electron from here to here without changing the energy, but giving a momentum which is large, which is like a reciprocal lattice vector. So, that is it's a huge change in momentum, but no change in energy, and that kind of situations lead to instabilities. And one of these instability that I discussed is this one, which I called Peier's instability, where what I showed is that if you have a regular lattice of this kind, that for example, in one dimension, in low dimensions, that has a tendency towards forming a distorted lattice of this kind. From here, this kind of distortions take place, and it leads to a dimerization, and that is so what we are saying is, in terms of band structure, we started with this kind of a band structure in one dimension, for example, and we are half filled. So, our Fermi level is here. So, again epsilon naught is said to be 0, epsilon naught is 0. So, these are all field states at half filling, and then this is for this kind of a geometry. So, this is pi by a minus pi by a, okay, and this is the distance, lattice constant is a. So, what this distortion does is that, for example, it will bring two of them closer alternately. So, you can move this one, for example, alternate site, alternate lattice site, alternate atom to the left or to the right, it does not matter. This is an infinite lattice. So, you can do it either way, they are equivalent. Now, this means that your unit cell is now the lattice constant is now twice A, okay. And this kind of thing means that your Brillouin zone has now become halved. So, let us go back to the picture that we drew earlier. In this kind of situation, 2 atom per unit cell, you will have a this band is going to change to a band like to 2 bands which are like this. And remember how many states we had here? We had n states. How many states we will have here? We will still have n states, because the number of orbitals have not changed. This is n is still the number of orbitals. What has happened is that the lattice constant has doubled. So, your Brillouin zone boundaries are now at pi by 2 a and pi minus pi by 2 a, and you have n by 2 states here and n by 2 states here, still n states. Because the Brillouin zone has halved, you have half number of states k values available for you. So, each of these bands will carry half the number of states. So, how many electrons can n by 2 states accommodate? Well, it can accommodate n electrons. So, I still have n electrons, number of electrons has not changed. So, I will accommodate n electrons here. Now, let us compare these two graphs. This one, for example, the top one here is a metal, because you have states available up to this, all these states are empty, and there is almost no gap at the Fermi level. So, this is the Fermi level. Here you have become it has become an insulator. So, this is a situation which is energetically favorable for it, and it has gained a large amount of energy by pushing down this occupied part of the band down from here to here. So, there is so each of the electrons are gaining a lot, each of these n electrons have now gained a lot of energy, electronic energy, and that means this is a more stable state than the previous one. Of course, if you have a distortion, that distortion is always, that means that there is a lattice is strained. So, the lattice of course will contribute positively to the energy, lattice energies will go up. So, that is kind of half k x square energy that will have to be added, but you can actually do the calculations, and it is almost always that this electronic energy wins in a low dimension, and therefore, what Peierls showed was that he added the electron lattice coupling to it to the theory also, and he found out that this kind of an instability is rampant in 1 and 2 dimensions, and so this means that a freely floating one dimensional lattice without supported by anything is very hard to stabilize. It will tend to dimerize or lead to some distortion, so that the energy is gained, and often it becomes an insulator. Similar thing happens in 2 dimensions. One example I have just shown on the left, that is this kind of a situation where if you have this flat regions of the band, then you have then of course, you have a propensity for the system to form to distort the lattice and obliterate the Fermi surface, basically make a gap, produce a gap at the Fermi level. So, this is a one route by which you can have an insulator. Of course, in this purely band picture, you can have an insulator simply by having two bands. For example, if you have just two bands, say for example, one coming from your s orbitals and another coming from p orbitals and so on, you can have two sets of bands. One is occupied and then there is a gap, and so these are all occupied states. You have to excite an electron, you have to take the electron from here, that is the minimum excitation energy, then you have to put it here, and that means there is a finite energy required for the electron to be shifted up, and that is a situation which is basically you can see that it is nearly incompressible, and to put even to change the number of electrons by 1, you have to have a finite energy. Suppose you want to put in an electron from outside and make it n plus 1, then you can only go here at the top band, at the bottom of the top band, which is empty, and that means there is a gap to that. So, a finite energy is required to either excite or add an electron to the system. So, this is how in the band picture, the picture that I have just shown you, this is how metal to insulator, metals and insulators or semiconductors are distinguished. It is simply a single particle levels, where you have two levels, two bands formed out of two different sets of orbitals. They can mix also weakly, sometimes they weakly mix, because orbitals are not orthogonal at different sites. So, but then finally, you will have the number of states remains the same. So, you started with two orbitals per side, you will get two sets of bands, and if there is a gap in between them, and if your filling density is such that you fill the lower band and keep the upper band empty, then you are having an insulator, and that is the picture of formation of an insulator in the in any of the band structure theories that one does. Of course, the band structure that we did is the simplest. So, this is the tight binding. In tight binding, approximation, you saw that for a square lattice, for example, E is minus 2 t cosine k x plus cosine k y, E of k x, E of k. Now, this is a, I have again set epsilon not equal to 0. So, this is the simplest, for example, for square lattice, for a square lattice, this is square lattice with A equal to 1. This is the band structure, and then and T is the hopping matrix element. So, this is the simplest that one can do, and from this simple picture, one can get a lot of insight about the nature of the material that one is considering, whether the material is an insulator or a semiconductor, and so on and so forth. So, this kind of very simple pictures, it can also tell you about the Fermi surface. For example, these are Fermi surfaces for BCC and FCC lattice. So, if you know the density, if you know how many electrons you have to accommodate, and then you calculate a band structure and just fill up the states. So, that is the beauty of doing this single particle physics, because you will be solving the Schrodinger equation for only one electron in this entire set of orbitals, and in this the Hamiltonian that we wrote down, and then you obviously you neglected the electron interaction. You also took the Born-Oppenheimer approximation, where the nuclei are considered fixed, and under that approximation, particularly the without any interaction between the electrons, this is the way one has to go about solving the band structure. There are more complicated ways of doing the same thing. There is a method, already well developed band structure methods, that is a very sophisticated technique, but ultimately at the end of the day what they do is still calculate the single particle energy levels and put particles at those energy levels, and that is still the procedure. And if you there are so called density functional theories and so on, which are very celebrated theories, earned a Nobel Prize also, and there also people try to take care of certain kinds of interaction between systems, but at the end of the day it is again a single particle picture in which you have single particle levels which you have to fill up starting from the bottom. Now, of course, this is as an aside, this is not the only method by which you can get an insulator from a metal. There are two more well known categories, which are one is by disorder. So, insulator by disorder, and the other one is insulator by interaction. The first one was worked out by P. W. Anderson, and the second one had contributions from many people, but this goes by the name of Mott transition, where in the first one what happens is that if you put disorder in the system, of course, the calculation that we did, the Bloch theorem that we used, those are usable only if you have a perfectly crystalline system. If you deviate from perfect crystallinity, suppose you put some defects, some substitutions, or some defects that naturally creep inside a system, then you have no choice that there will be some effects of that, and that effect can be dramatic in dimensions less than or equal to 2, and that was shown by Anderson and collaborators. And what they showed is that any finite disorder in dimensions 2 and below can have catastrophic effect, and in 3 dimension they can also have effect depending on how strong the disorder is. There are many kinds of disorders, not just defects. You can have boundaries, you can have domains and so on and so forth, or external impurities, or damage by radiation and so on and so forth. So, all kinds of disorder, but all of them will have the salutary effect that in dimensions 2 and below they can change the nature of all the states dramatically. These are still single particle states. These states dramatically change their character, and that is that these states are no longer extended states like in the Bloch theorem that we got, plane wave extended states. These become then localized. So, the nature of the states change, and that is called the Anderson mechanism for Anderson's mechanism for disorder induced metal to insulator transition. So, as you increase the disorder slowly and slowly, the states start to become localized, and this in 3 dimension at a critical disorder you will finally localize all the states, and then no state will span the entire system. Remember, the plane wave states that we are studying with, they are equally probable to find almost everywhere in the system, because they are plane waves. So, these states are they are everywhere. So, that nature has changed, and the state that one lands up with disorder are localized, they are exponentially decaying, and so that is one mechanism by which you can have a insulator from a metal, starting from a metal. There is another one which is much more complicated, which is, as I said, is driven by interaction between electrons, and this is of course not described in the same way that we did this band structure calculation so far, because now because you have interactions, you cannot write a wave function of a multi-particle system as a product wave function starting from single particles. So, this filling of bands, this filling of levels, and the idea that there are single particle states breaks down in this when interaction is present, and this leads to a very dramatic new physics in the in many systems, particularly systems where the electrons are in 3D or 4D or 4F or 5F levels, the valence electrons. There the electrons are tightly bound to the nuclei, to the parent atoms, and so the effect of interaction is dramatic, because their bandwidth is low, and it can lead, as the interaction increases, one can completely lose this single particle picture. So, that is a completely different scenario, and we will not discuss it further, but I just want you to remember that there are other mechanisms by which insulators can form, which is one is this insulator by disorder, another is by interaction. Then of course, nowadays you must have heard of things like topological insulators and so on. These are fairly advanced topics, they are interesting. These are some of these topological insulators, for example, are insulators in the bulk, and they have metallic states at the surface. So, and these are the effect is dramatic also here, and there are lots of very interesting physics that are coming out, but we will probably discuss those things at a later stage when we discuss some advanced topics towards the end. But at the moment, let us just let us just remember that there are these new states that are new physics that is coming out, and this way of doing physics with electronic physics with only the conventional band structure works very well in most systems, in many systems, but it may fail in certain cases, and that is where some very interesting new physics has come up in the recent years, and for last 50 years or so one knows these other routes of metal insulator transition and so on. Those we will not discuss in this course, but topological insulators we might discuss as an advanced topic towards the end.